Okay, good afternoon, everybody. So I'm going to talk about how we can detect software performance regression using machine learning techniques, more specifically using deep learning techniques. This project is supported by the Software Center, and interested companies are Volvo Cars and Bosch, who supported us in this project. So I'm going to explain the process, how we start to tackle this problem using deep learning techniques. Before going into the specific solution, so we are mostly interested about the program analysis based approach. And so before going into the definition of this problem or formalization of this problem, so I start with saying that there are three kinds of program analysis that we usually do to solve many analysis tasks. So the first one is the static program analysis, which basically do not execute the code, but this kind of analysis generates what's called a mathematical model of the software and collect facts. And afterwards, different kinds of logical inferences are done to get the solution of the problems at hand. Examples of such analysis consists of data flow analysis, abstract interpretation, formal methods, model checking, separation logics, and so on. And the second kind of analysis, which is also often used, is the dynamic program analysis. And in this kind of analysis, the source code is basically executed in a controlled environment, and before executing the source code, it is instrumented to instrumented the code to monitor different kinds of program parameters. And then by monitoring those parameters, different informations are gathered, and then the solution is provided with further analysis. So examples of this kind of analysis includes, for example, service-based program analysis, program profiling, even program testing falls into this category. And then the third kind of analysis that I will talk about today is the neural software analysis. And in this analysis, basically, if program code is represented using some kind of program language models, which is learned by using different kinds of artificial neural networks, and then different based on the training and testing and validations. So different solutions are predicted afterwards in the testing, after testing and after the validation tasks. So we'll see to solve this performance regression problem, we'll use this kind of neural software analysis. So what is the problem? So nowadays, small or large organizations use distributed version control systems such as GitHub or GitLab to develop and maintain the software. And each developer in this environment basically maintains a working copy of the software, where he or she add features of the code, add different kinds of features of the software, fix bugs, or upgrade the systems. And then they perform local tests, and once they are satisfied, what they do is basically they commit these changes into the main repository to reflect the changes. So what happens is that during these changes, the push of the local updates may introduce performance regression in the master branch of the software. And this is propagated later on into the working copy of other developers, or even into the released version of the software. So performance is one of the major critical non-functional quality attributes of the software, and performance regression happens when the software under tests or software under consideration consumes more computing resources, such as CPU time or GPU time, memory, network bandwidth, etc. During the development phase, some performance regressions are expected. For example, developers might want to add features to the system which may consume more resources, and this is expected. And we call this kind of regression benign. But then there are other kinds of performance regression that is totally unexpected, and we are more interested to detect those kind of unexpected performance regression into the system. So then I will talk about three different kinds of related problems related to performance regressions. Um, so the first one is the software resource analysis, which is a kind of which is based on static program analysis basically. And in this problem, what happens is that uh, so different kinds of source code, they are analyzed, and different kinds of recurrence equations of the software are generated. Or for example, if the technique is based on resource aware type analysis, which generates resource constraints, and then these recurrence equations or resource constraints are later solved by using a special kind of solvers, and that generates this kind of symbolic symbolic equations, for example. And in here you see all the equations are polynomials, but this kind of software resource analysis, basically they can generate any kinds of equations, like it including exponential and logarithmic expressions. And that for here the double how is it called, the double bar here indicates that this is a max of 0 and m, because resource cannot be negative. So it the expressions in this kind of category always involve this kind of expressions. And so by using different kinds of static techniques, we can generate such kind of symbolic equations, equations representing resource consumption of the software. Okay, now if we can generate such kind of symbolic equations of two different versions of the software, probably we can compare those symbolic equations, and then we can say if a particular version of the software introduces performance regression or not. So this is a one potential solution for detecting performance regressions. But then the problem is that you see this kind of symbolic formula, it is very hard to manage when we generate such kind of formula from a very large software systems. This kind of formula gets very, very complicated at some points. So this is the first problem. And another problem is that the results may not be precise. Also, to generate such kind of symbolic formula, the whole software needs to be analyzed every time for every commit, which can be very time consuming. So this was the first approach that we decided not to go for it. Then the second approach is it is called software performance testing, which is basically done in the industry many times for how is it called, for performance critical softwares basically. And this kind of testing includes, for example, load testing, stress testing, scalability testing, and so on. So the general idea of this kind of testing is that this software comes with some kind of testing benchmarks, which are these benchmarks are used to perform these testings to check the properties of the system under various execution scenarios and check different properties such as responsiveness, robustness, and stability, and so on. So this for performance critical softwares, I mean, there is a schedule to perform this kind of testings. For example, it can happen that every night the performance test will be performed, or after every X number of commits, or every major, for example, event, after every introducing some features, and so on. I mean, this kind of performance testings are always scheduled there. However, these performance testings are very costly in terms of computing resources, and takes a lot of time to finish the testing. So it is not feasible to do the testing at every commits, or at every changes that is done on the software developer's working copy. So we need a better alternative, a better lightweight alternative to detect if a local changes in a version of the software introduces any performance regression to the master branch or not. So the third kind of related problem, which does not look very much related, is called code clone detection. And the idea of the code clone is that what happens is in the industry is that many developers is many times what they do is they copy a piece of code from one place to another, and then they modify the copied code to meet their demands. And there is a very much similarity between these two piece of code, and then we call them code clone. For example, here these two pieces of code are very much similar, uh, basically exactly the same, except introducing the method call here, which may introduce performance regressions. And there are different types of clones. For example, there are type 1 clone, which where the both pictures are exactly the same. Non-syntax tokens are only different, such as, for example, they may introduce comments or other things. Type 2 clone is similar to type 1, where variable names may be changed, for example. And type 3 is similar to type 2, but there may be addition or deletion of statements in both clones in the code snippets. And then the type 4 clone, which is semantically identical, that means they are computing similar things but not necessarily same syntax. So these kind of definitions of different types of clone exist in the literatures, and some of them are not very formal, we see, but there is no formal definition of code clone in the literature. So the question is how this code clone is related to software performance regressions. So you see, what we do is basically in a code clone we compare similar pairs of code to see if there is any kind of similarity or not. In the distributed development environment, in order to understand whether there is a performance regression or not, what we do is basically we look into the similar piece of software. But of course, we look for different things. For example, in the code clone, basically it is more for at least for type 1, 2, and 3, they're more interested about the syntactic nature of the code. But in case of performance regressions, we are more than that. We wanted to see if I mean, basically what happens is the two piece of code, developers might change here and there, and then so they look similar. Basically, if we expand the granularity of the clone, basically the two versions may be cloned to each other, but some of them may introduce regression, some of them are not. So I mean, the underlying mechanism to detect if there is a clone or not, or if there is a performance regression or not, are similar. Especially similar in the context of machine learning, because in both cases they learn the they learn the representation of the source code in a machine learning understandable format, and then they learn different kinds of prediction functions. So for code clone, maybe the machine learning model will learn one kind of function, but for understanding performance regressions, the machine learning model will have to learn different prediction functions. But that is the problem of machine learning. I mean, we give the mechanism to the machine learning model, and then the prediction mechanism will be learned by the model itself. So, so there is a kind of similarity between the detection mechanism of code clone and the performance regressions. And in this project, software center project, basically, I wanted to use the code clone detection mechanism to detect performance regressions. So why? I mean, I already have discussed why, but then the question is why this kind of machine learning based technique is good to detect performance regressions. So in a previous talk, I mentioned this figure where which problems are good at, which problems should be solved using machine learning. There are three dimensions. The first one is if the problem is well defined or not. The second is if the available information to detect the to solve the problem contains uncertainties or not. And the third dimension is, do we have sufficient amount of data to train the machine learning model? So a problem that is not so well defined, has high degree of fuzziness, and has large amount of data for training, uh, are best suitable to be solved using machine learning techniques. And if we look into the performance regression prediction model, um, then we see that, for example, the performance regression problem is not very well defined, because we don't know when the performance regression happens. There can, we know for some we know few cases, but not all the cases. So in many solutions, for example, they introduce patterns of code changes that may introduce performance regressions, but that is not how is it called, that is not the whole solutions, that is only a part of the solutions. And then there are fuzziness of the information. For example, some changes may introduce performance regression, where some other changes do not introduce the performance regressions. Maybe a change of the name of the variable sometimes introduce the performance regression. So there is some kind of uncertainties here. And we can generate a lot of training data, because, for example, many projects have their test benchmarks. So we can utilize those benchmarks to generate test data. So we can use machine learning techniques to solve this kind of performance regression problems. And like in any other machine learning solutions, we will apply 3 stages of the like it will have 3 parts. For example, the first part will be the pre-processing part, where we select the source code or the source code from the repositories that on which we will try to learn if the changes will introduce performance regression or not. Then we need to generate the labeled data from this source code. And also we need to generate a vectorized representation of the source code, because the machine learning model only understands vectors of numbers. So we need to transform this source code to some kind of vectorized numbers. That's the that goes to the pre-processing phase. And then once we have this thing, we have this level data and the vector representation of the source code. We give this to the different kinds of artificial neural network architectures to learn different kinds of parameters of the model that will for example, that will control the behavior of the artificial neural network to learn the prediction functions. And once it can learn, then we can use the test data to predict the software performance regressions. So what we did for pre-processing, for example, in this project, what we considered the Git repository mainly, because it is an open source project, and the source code is available. There are performance testing benchmarks that we can use to generate labeled test data. And so what is done is that performance tests are done to generate the labels, and we from initially 8,596 commits, we generated 9,551 pairs of performance tests, and they are compared. During this comparison, we discard some data because, for example, branch merging commits are removed. It may happen that when a branch is merged, they often introduce performance regression, but that can be expected. So we remove those kind of parts. And commits that only changes, for example, documentation or other kinds of files, not the source files, we also remove those kind of commits. So we ended up with this number of 9,551 pairs of commits, and we get this kind of database where we have two different kinds of commits, commit A and commit B, and we have labels 1 or 0. Basically, this should not be 5, this should be 1 or 0. And we have a label saying if we have a performance regression or not. Then we can happen that for a pair of commits, we have multiple entries into these databases. So that's because for two commits, we can have multiple performance tests. And then at least if one of them gives us a 1, that means there is a performance regression, then we say that the two commits has a performance regression. So after removing all the duplicates from this database, we are left with 708 unique commit pairs that we have used for training, validation, and testing. So what we did is that then now we have a database saying we have commit A and commit B, and then we have a label. So what we can do is we can generate the source code representations, vectorized representation of the source code for the both two versions of the software. But the problem is that it will take a lot of time for training and testing and validation if we use the whole use the representation of the whole software. So what we did is basically we check between these two commits, what are the files that are changed, and we also considered those commits where the change of source files are less than 10. Because if the changes of files are more than 10, we considered that the performance, there may be performance regression, but that are desired because probably they have introduced some kind of features into the systems. So we don't care about those kind of regressions. And then what we did is that then we see the changed files, we merge all of them into a single file, and then we used Clang to generate the abstract syntax tree of the merged files. And then we used word2vec model to generate the initial vectorizations. And word2vec is a popular algorithm, for example, which is developed by Google in 2013 in the in understanding natural languages. But we have used this here to generate the initial representation of the source code. So what we are left is at this phase we have, for example, for commit A and commit B, we have a vectorized representation of the abstract syntax trees in both commits and the labels. Then the next step is how to train this model by using different kinds of mechanisms. So before going into that, what we did is basically, for example, once we generate the abstract syntax tree here, and we cannot use directly only word2vec here to get this kind of vectorized representation of the tree. So what we did is that we search this tree in a depth first or pre-order traversal manner, and generate sequence of, for example, sequence of nodes here. For example, each sequence represents each statement into this tree. So basically this tree here, you see in this function, we have two statements, one if statement, one return statement. Once we transform this code to an abstract syntax tree, we have these two statements, subtrees. This subtree represents the if statement, this subtree represents the return statement, and this subtree basically represents the parameter of the function. So in this way, we generate the sequence of nodes representing different statements into the code. These sequences are then, for example, we use word2vec model that contains some kind of embedding of the source code tokens and the abstract syntax tree token. And then we replace the tokens by the vectors to generate the vectorized representation of the code. Once we have this, for example, these statement trees, then these are the vectorized representation of the tree that we have generated in the earlier stage. Then we give this tree to the statement encoder, which is a kind of recursive neural network based encoder, which basically utilizes these functions, these two functions basically, to generate some kind of encoding of these trees. And what they do is they recursively traverse the statement trees and learn the encoding of a node from the encoding of its child nodes. So we use this mechanism to generate the first layer, this kind of encoding layer, which generates this vector. Also, these are also vectors, so vector representation of the code, which is later these vector representations are given to this kind of recurrent and pooling layer, and they use. This is the method we used from this work. They use this method for port colon detection. Uh, so we wanted to see how it works. So then we used bidirectional gated recurrent unit in this stage, and then we applied max pooling to generate a representation here, which basically represents the whole system, represents a particular commit. Then not basically particular commit, because we do batch processing. That means we take a batch which contains abstract syntax tricks of multiple source files, and so these are basically represents the it gives us the representation of the whole batch. Then we compare the two different representation of the two commits, and ask the model to learn a function to predict if there is a performance regression or not. So that's the underlying mechanism. What we did is, this is still a work in progress. So we have implemented the first version of the tool, which is now available in GitHub, which has some problems and some solutions. So for small programs, it can give us the model can really learn the performance regression. The neural network model. It learns the performance regressions. But when we give the big files from the of the Git source code, what happens is that because the changes can happen in multiple modules or multiple source files, and the abstract syntax tree that we get from such representation is really huge. And when we give this the vector representation of this tree to the neural network model, at some point it exhausts the computer memory. And we already have solved this problem. Basically, what we did is we break the large trees into subtrees, where we now give, instead of giving a whole abstract syntax tree, we give one abstract syntax tree for each function. So in this way, we divide it into, the bigger problem is divided into smaller sub problems, and then we merge the results. So this way we have solved the memory exhaustion problem. So the final version of the tool, we expect that it will be available shortly in the GitHub. In this GitHub, we will commit it by the end of June. So we still have 2 weeks left of this sprint, and then we will solve it there. Then afterwards, once we have this final version ready, then we intend to perform the how is it called, experimental evaluation of how this tool is doing on our test data. And then but then it's time also for the sprint 21 to start, and then we have submitted a proposal to extend this work. And the idea of the extension is that, okay, so for this work we have used abstract syntax tree based language models of the source code. Then because now there are more advanced language models, such as, for example, graph neural networks, and graph is very good to understand the execution scenarios. What executes after what. This kind of scenario can be captured by graphs, for example, control flow graphs or program dependency graphs, which basically captures who is dependent on what at particular execution scenario. So our idea is to we will augment or replace this tree-based neural network by graph neural network, and then we will compare their results. Which one is good? At what scenarios? That's the idea. And then also the second another thing is that this software, this neural model that we get from this kind of solution is not only can solve the performance regression, but they're also very good at solving, for example, bug regressions. There can be developer might introduce different kinds of bugs into the systems. And we believe that this kind of model is also very good to capture those kind of bugs that that is introduced into the systems. So that's the idea, that in the next sprint we will apply this kind of models for bug regressions. And then also the idea is to produce scientific articles based on our evaluation on bug regression and performance regression. So that's the idea for the future work. And also I'm looking for collaboration. So if any of you are interested here, if any of you are from companies and interested to support this work, please let me know. And that's all from me. Thank you.